Hi, my name is Dazin. I'm a second year PhD student from University of Technology, Sydney. I wrote this research paper with my two supervisors, Yudesu and Manuel. First of all, I would like to give special thanks to both of my supervisors and all the reviewer and committee from ICPC conference who supported and gave me the opportunity to present this paper in this conference. To start off with, this paper is about a literature review of automated traceable link recovery approach in the area of software chain impact analysis. Basically, we analyze and summarize previous study which mainly focus on automating the trace link recovery approach to support the software chain impact analysis activity. In this presentation, I split up the session into 6 different parts in order to share the in-depth information about the paper. And then I will start off with background and motivation and discuss the main finding. And lastly, conclude with recommending the future work in this context. In terms of topic, these days in any software development project, we all know that changes are inevitable and rapidly changing as well. So to keep up with the demand, the most common mistake software development team do is jump straight into the implementation without analyzing the current state of the system. So as a consequence, in worst case scenario, it introduces a failure error in the system and costly as well. So this is where chain impact analysis comes into play. Just like a diagram on the right corner, software artifact like requirements, source code, and test cases are the most changes area in the system. So chain impact analysis process in general is trying to identify the link between and assess the overall effect of the system by recovering the link between various artifacts and then study the effect prior to the implementation. Therefore, it reduced the unnecessary error in early phase of the deployment. Although it sounds simple, but in real life, it is hard to do chain impact analysis manually because it is time consuming and error prone. So in recent years, there is a growing body of research focused on automated traceable link recovery process to speed up the chain impact analysis process. And we are aware that there are various ways to recover the link between software artifacts automatically. So we want to find out more about what are the main difference between this approach and what the challenges in automating them, and so that we can identify the gap for the future work. In terms of existing work, similar to our work, we found 3 previous studies which focus on trace link recovery approach. As present in the figure, the first 3 gray blocks represent a previous review paper and its time frame, and also the green block is our paper. The first paper from Marcus Port especially focus on analyzing what type of IR model, information retrieval model are used in recovery link between software artifact. And the second Javid paper reported the finding on how previous study recovered the link between architecture and the source code. The last review paper report the summary of various traceable link model. So to the best of our knowledge, our paper is the first review paper which focus on automated traceable link recovery process in relating with chain impact analysis activity. The aim of the study is to systematically review previous study which focus on automated trace link recovery approach in relating with chain impact analysis context, and then identify the research gap to derive the future research direction. In this paper, we focus on answering the 3 research questions. The first question is about analyzing the traceability approach. And the second question focuses on answering which part of the chain impact analysis process are supported by the automation. And then last question is focused on transitive tracing approach. And we want to analyze in which scenario transitive tracing is applicable for. To perform our literature review thoroughly, we follow the systematic literature review guideline provided by the Kitchen and Charter. And in first phase of our review process, we construct a search string like this one, and also below to cover all the synonym and a term related to our context. And then we ran our search in 5 different databases to mitigate the bias in study selection. So we selected the 5 different databases like IEEE, ACM, Science, Rise, Springerlist, and Scopus. And these are because these are all scientific publication and peer review as well. Also, we deploy the study selection criteria as below, and according to filter the publication according to the relevancy of our context and verify the paper follow appropriate research method or not. In terms of time frame, we select a study published within 2012 and 2019. The figure on the right illustrate how we conduct our research process. First, we scan the title and filter out the irrelevant one, and we end up with over 2,000. And the next step, we scan the abstract of the selected paper according to our selection criteria. And the last scanning step, we analyze the contents of the paper in depth and extract the information according to our data extraction criteria. And also, we conduct forward snowballing on the selected paper, and I found 4 more additional paper, so added to our finalists. So in total, we included 33 studies in this review paper. So the following section provide the detail about the main finding. We created this training diagram for this 33 study based on the traceability approach and the type of artifacts supported in the study for visualization. Internal traceability approach, we found 4 traceability approach in this study. First one is an information retrieval based approach. Most of the IR study recover the link between 2 artifacts based on textual similarity score. The next one is a heuristic based approach, and the third one is a machine learning, and the last one is a deep learning. So in terms of artifact, we found 6 different artifacts experimented in the study. We also use different color for each artifact. Also added this artifact in each approach panel to illustrate what type of artifact are supported in the study. As you can see from the publication here, the majority of the study use various IR approach, and most of the study experimental with requirement and source code and a bug report. Only the few studies use a test case to experiment the approach. And also, interestingly, we found a couple of heuristic-based approach. And in recent years, starting from 2017, a few studies experiment the concept of machine learning classification, the approach to leverage the IR-based approach. And we also found a handful of studies that use deep learning-based approach as well. And lastly, we found a new artifact called feature. A feature is a brief description of the system module and functionality. And we found a study that used a feature as a transitive artifact to establish the link between requirement and source code. Next one is a traceability tool. We found 5 traceability tools introduced in our primary study. The first 2 is a trace me and a retro. These are the special purpose tools which focus on tracing between requirement and the source code and test case. The middle one is a SPL trace, is a general purpose tool which provide a framework to build traceability model. And the last 2 is TraceLab and OpenTrace. OpenTrace is a workbench tool which provide a space for researchers to experiment traceability project. Internal trace direction, we found 2 types of trace direction, and the trace direction are experimented in the study. As you can see from the donut chart on the left, majority of the study validated their approach in unidirectional way by recovering the link between 2 artifacts in either backward and forward direction. And only the 6% of experimented their effectiveness of their approach in bidirectional way. We further evaluate the primary study based on their research method and test project as well. So as illustrated in these 2 charts, majority of the study are experimented study and evaluated their approach either with open source or university data set. And only handful of study performed the case study and evaluated approach with industry data set. In terms of chain impact analysis process and which part of the chain impact analysis process are supported by the study, we use 4 chain impact analysis sets provided by Bona chain impact analysis model and cluster this study. For example, the first one, requirement impact set. If a study user requirement as a source artifact, target artifact in their tracing approach. Then we used this study to, we included this study in this cluster set. And the table on the right represent the summary of the finding. As present in the table, majority of the study focus on program impact set because it is the most frequently changed area in the system. And the requirement impact set is the second highest group in the category. And lastly, only the handful of study focus on test and design impact set. The last finding is trace link recovery method. We noticed that there's two ways to recover the link between two artifacts. One is the direct tracing. The direct tracing, this method is applicable for explicit tracing when the source and target artifact have shared the high textual similarity. And another one is the transitive tracing. This method is applicable when the source and target artifact don't have a high textual similarity between them. So it uses that artifact as a transitive artifact to recover the link between source and target artifact. As illustrated in the figure, the majority of the study used direct tracing. Only a handful of study evaluated the approach with transitive tracing. To recap our finding, the majority of IRB study use VSM, LSI, and LDA ideal model to recover the link between artifacts. Most of the study use VSM as a baseline mechanism to compare their compare with their approach. And also we found out that requirement, source code, and bug report are the most frequently linked artifact in the study. And internal chain impact analysis set, most study focus on program impact set because source code are the most frequent chain area in the system. However, few study only focus on recovering the link between design and test case artifact. We assume that probably because of the unavailability of test data. And also we noticed there is no study focus on end-to-end tracing to support the overall chain impact analysis process. Only the direct tracing is only applicable when the source and target artifact share the high textual similarity. And lastly, we noticed we aware that there is no traceability to do that support the transitive artifact approach. So in terms of future work, we think researchers should more focus on enhancing the tool to support fully automated traceability recovery approach, and the tool should focus on machine learning-based approach and deep learning-based approach to increase the accuracy in establishing the link between two artifacts, and also it should emphasize on recovering the link between modern artifacts, software artifacts like user story, accepted test case, and the source code, which are commonly used in agile-based software development, and also rather than only focus on test-based recovery approach, future work should focus on wider media like images. Some of the artifacts can be created in image, so traceability should support these artifacts as well, and also investigate more on static program analysis or pointer analysis to provide a precise level of impact area in the source code. And lastly, we would like to recommend to evaluate more on the industry data set and then survey practitioner to gain insight about their feedback for future improvement. So this is the end of my presentation. This is the references, and thank you for listening.